All right, let's keep plowing through Chapter 21, which I hope is providing some interesting new organic chemistry for your synthetic toolbox, but also providing a fair amount of review. Where are we? Well, I guess the most important thing that has come from Chapter 21 is learning how to get to the top of the reactivity ladder so we know how to interchange all these carboxylic acid derivatives. So I now know how to make acid chlorides from my carboxylic acid, and from acid chlorides I can make just about anything. Now we should understand in some detail the reasoning behind the relative reactivities of all these carboxylic acid derivatives, resonance and electronegativity, good review of old concepts. And I'll admit we've thrown in a few new reactions that are pretty useful. The Baeyer-Villiger, how to make tosylates, fantastic leaving groups for alcohols. And everybody's got to love the Hell-Volhard-Zolinsky just because of the name. So what's left? Well, that's a really good question because, Chapter 20 and 21 are really still all the same mechanism. The old up, down, and out. Always going through our friendly tetrahedral intermediate as shown here, and balancing the reversibility of all these reactions, looking at the equilibrium between kicking out that anionic leaving group in this example and comparing that to the stability of the incoming nucleophile as an anion. So what can we do to summarize what we've learned so far? We've learned that there's a boatload of different leaving groups, and that really explains the reactivity ladder. That halides and acid chloride derivatives are fantastic leaving groups, and so acid halides can readily react with a variety of nucleophiles. But even acid anhydrides, which of course would kick out up, down, and out, kicking out this guy, the carboxylate, that's a fantastic leaving group too, right? Minus very weak base with that minus charge, easy peasy. So anhydrides are also highly reactive. So we've seen a lot of different leaving groups in this chapter. And of course we've seen a lot of different, or we'll continue to see different nucleophiles. I mean, at this point in our OChem career, we should just be able to rattle off a whole bunch of leaving groups, a whole bunch of nucleophiles, and put the pieces together and see what we get. So what nucleophile haven't we added to our carboxylic acid derivatives? And that nucleophile is this nucleophile, the enolate. Now, we studied the enolate, oh my gosh, so long ago. The first time we looked at it was just in the acid-base chapter, knowing that it's pretty easy to form an anion on the alpha carbon. And you know what? We looked at an enolate in terms of addition to this electrophile in chapter 17 and 18. In other words, the aldol. What's different now? When I add my enolate to a carboxylic acid derivative, we know we get the same tetrahedral intermediate, we get the up, down, and out, and we get that leaving group, as usual, to be kicked out, which gives us a 1,3-diketone. So, it's the same mechanism, it's the same tetrahedral intermediate, but the product is invariably a 1,3-diketone. Now, what pushes this equilibrium all the way to this stable final product, the diketone? Well, the fact of the matter is, if it's easy to deprotonate an alpha hydrogen because of resonance, it's even easier to deprotonate one that can be delocalized between two carbonyls. So the fact that we have a diketone here with a CH2 group in the middle, that's a 2, that makes this a very, very favorable deprotonation. And again, kind of like saponification, we see that last step's a doozy that makes the Claisen, this particular Claisen, irreversible and very much favored. Alright, so this is called the Claisen condensation. Be forewarned that there are Claisen condensations and Claisen rearrangements, and we will not learn Claisen rearrangements, so just forget about that. Alright, so the Claisen condensation officially is the enolate of one ester reacting with another ester as the electrophile. Alright? It could be a self-Claisen condensation, just like we saw self-aldols. But really, if you have the enolate that can add to an ester, we'd call that a Claisen condensation too. So, bottom line is, enolate plus ester gives you a 1,3 dicarbonyl. So again, here's an example of a self-Claisen. So as long as you have an ester with an alpha hydrogen that can be deprotonated, then you're going to have an enolate. And of course you'll ask yourself, okay, now I have this enolate, what can it do? Well, if there's nothing else around, then it can react with the only electrophile that's present, which is the original starting material. And in an up, down, out, we see that we get our 1,3 dicarbonyl. That's our Claisen condensation, because we have spit out a small molecule under basic conditions, this alkoxide. So that's the Claisen. And just like the aldol, there can be good Claisens and not so good Claisens. So we want to avoid the crossed Claisen. This one would be a thoughtful Claisen, a good Claisen. Why? Because I don't have an alpha hydrogen on this ester. I do have an alpha hydrogen here. So there's only one possible enolate that can be generated. So CH3, CH minus. Here's my ester enolate. It can now react with this electrophile. So nucleophile meets electrophile, up, down, kicks out my alkoxide. So that gives me, there is the original electrophilic CO. What reacted was the enolate. So here's my new bond. This is my enolate carbon. Here is my rest of my molecule from this guy. There's my Claisen. 1, 2, 3, with the two COs, 1,3 to one another. Again, emphasizing that relative positioning is a big tip-off of what kind of chemistry you can use to make a molecule that has this functionality. Alright, how about this example? Well, looks like I've already generated my enolate, so I know this is my nucleophile. What's my electrophile over here? Well, let's spell it out. I have a protected amine over here, and it looks like I have a stereocenter. But what we want to do is draw out the ester so I can see what's going on here. In so doing, I now can see that I'm going to come over here, up, down, out, and so my product should be this protected amino thing. Don't mess with the stereo center. I didn't do any chemistry there. And here's my enolate piece right there. That should be my product.